Today, I introduce about scalable bias resistant distributed randomness more detail. Before introducing the protocol, I'll just introduce a few of key points I introduced last time. First, availability is related to successful protocol termination. This model allows up to F malicious node, and this up to F, and this T value means VSS threshold. Unpredictability means that no participant should know the result in advance. And biasability means that the output distributed must form uniformly random. In other words, it shouldn't allow anyone to manipulate and bias them. And verifiability is an attribute that must be verifiable by a third party other than the participating member. Finally, scalability means that the protocol should proceed normally for many participants, like hundreds or thousands. In this paper, there are three concept protocol. First, land share a protocol that satisfies unbiasability, and unpredictability, and unavailability. This is only possible on small scale due to this communication overhead. And then next protocol is landhound. Landhound is a client and server-based protocol. When a client requests a random value, the server produces public, verifiable, and unbiasable randomness. Finally, landhound is a beacon that continues to generate a random using a landhound. Now let's take a look at landshare. As mentioned earlier, this has a larger communication overhead, so therefore it is only available for small groups. And this protocol output is unknown but fixed as F+1 inputs. And we assume that the Byzantine adversary and asynchronous network. That means message will be eventually delivered. So this F means dishonest PR, and this T means VSS threshold. And we set this value with T value as F+1, and we need more than 3 F+1 nodes. Also, we assume that every peer has a copy of public key of other peers. Now, let's follow the random share scenario. First step is share distribution. Now, let's follow the random share scenario. First step is share distribution. Every node makes their own polynomial for VSS using this SX equation. In the case, SI0 means a secret. For example, node 1 makes S1x like this and make value for distribute. And node 1 makes some x coordination for Sx and value about Sx and commitment for Sx's coefficient. Like this way, every node makes their own polynomial and distribute data. In this case, N1 makes 2 comma S2 and commitment for node 2, and 3 comma S3 and commitment coefficient for node 3. And to make commitments about coefficient Sx, they use this equation. And next step is share verification. This is scenario case about node 1. So first, make v vector for keep track of valid secret from other pairs. In this case, make a v1 for node 1, and this is consists of v11 v11 to v1n. This value initialized to 0 and wait until a message with share has arrived. That means peer wait until a message from other peers. And then verify each sji, in this case sj1, using a hat value. A hat value is made by this equation and verify using this equation. If verification is succeed, confirm sji, in this case sj1, by broadcasting prepare message pij1 positive message. This message means p means prepare message, and this I means received I from j. Verification is failed, then broadcast some pijsji negative message. And then if receive 2f plus 1 positive both for sj0, then broadcast cij1 positive message as positive commit. If there are at least f plus 1 negative both for sj0, then broadcast cij0 as negative commit message. And then if there are at least 2 f plus 1 commit message cijx for secret sj0, then set vij as x. If x is 1, that means sj0 is recoverable and else is invalid. Then wait for decision for RVI and determine the number of 1 entries in VI. Check number of 1 in VI and check if this number exceeds of S. If and that exceeds F, then broadcast for each 1 entry J in VI the share SJI and abort otherwise. And wait until at least T shares for each J has arrived and recover secret polynomial using Lagrange interpolation and compute S0. This means some secret value and compute collective random string concat using SJ0. This means concat, so collective random is completed by concat or secret from every nodes. Now we talk about random. This is some client and server model, and client requests random value to servers. And it allows f-1 malicious servers, and we assume that clients get only one attempt to run random. Using session configuration, dishonest client can't try to run protocol many times with same purpose. And this random improves random lack of scalability by grouping servers. It reduces overhead from O cube n to O n square of 2. This is random protocol overview. This right side shows some notation using in this protocol. This 0 means client, and this I means some servers. And this C means some session configuration, and T is a group configuration and indicates how the group is divided. U means purpose string, and this W means timestamp. And these values are included in this configuration. And Sij means share that send from I to J, and hat means encrypted. And Pij means proof that send from I to J, and it is used when Nijk proof. Also, hat means encrypted. And Aik means polynomial commitment, and HSIJ means commitment that is created at proof S with P and J. And these VI and C and R and E are used when Schnorr multi-commitment. And T dot means chosen secret, and TL means chosen secret of group L. And this Z means a random value, and L means transcript. First step is proceed in client side. Set value in session configuration C and choose RT as seed to create grouping of S. And then record C in L about this information. And make message include this information C and group T and purpose string U and timestamp W. And this message also recorded to L and broadcast this to all servers. Next step is proceed in server side. To distribute server own shares, each trust TI in group TI execute step 1 of PVSS. First, use hash C value as H in PVSS and set TL as this equation. This means some group threshold and make T-1 threshold secret sharing polynomial and commitment. And compute encrypted share using J public key and make encrypted proof using that public key. And choose VI and compute to logic VI for Schnorr commitment. And finally, send this R value back to client. Next step is in client side. Record all received R1 message to L, and all received SIJ is verified using PIJ and XI and AK through NIJK protocol, and save SIJ created in NIJK process. Mark that does not pass the verification as invalid. And receiving messages store a list of source servers that pass threshold of encrypted shares. Create a list of source server by randomly selecting this threshold size from those servers and make Schnorr challenges using these values. Concatenate of small v and hash of configuration and choose secret servers. And send these messages to all servers in same group. Now the server check that TL in T dot is a threshold size. Check all of this size is threshold in T dot. And check the sum of all TL is greater than F plus 1. And compute the Schnorr response using VI, their own VI, and these challenge values. And then response the Schnorr signature response. Client also record all received messages to L and compute Schnorr response using received RI. And create list of exception E that contains information about missing server commits and response. And send it to all servers using broadcast. When the server receives the message from the previous step, it verifies that C and R are properly signed for T dot. It is okay if there are two F plus one signature. Check every Sij value in TL dot, that is the encryption value sent to me, is verified using public key and at HSIJ. If the verification is succeed, it decrypt and create a decrypted NIJK verification value PIJ, and if the verification is fair, mark SJ as invalid and do not decrypt it. Then the calculated value are responded to the client. Also record all received messaging. Check each share as JI against PJI and mark invalid ones. After all message received, use Lagrange interpolation to recover S. Of course, we can't regenerate without enough threshold gathering. Create all of Si0 and then use these values to create the collective random values as Z using Si0 values. And then publish the result Z and the recorded L as a transcript. Now this is a verification step. In short, it is to run and verify all stored message again. First, check the config values to make sure that X is set correctly and that the size of group and threshold are set correctly. And then verify all signature of these messages and verify hash values that are proof that all messages are linked to previous message. So H1I matches in RI1 and H2I matches in RI2 and like this way. And make sure T dot has more than F plus 1 encrypted share and that cosine is 2F plus 1 sign. The encrypted value as IJ selected in T dot is verified using PIJ and XJ and AIK. Decrypt value SIJ is verified using PIJ. Make sure that it is the same as the last save Z and the generate Z that you follow these steps. Now, review the previous 4 indicators to assess land hound. First, availability means that the protocol should be terminated normally and a random Z is provided with high probability to honest client. And unpredictability means that nobody knows the final output Z before the final output except for a very small probability. Unbiasability is about that secret should be unbiased except for a very small probability. And verifiability means that the random Z value should be verifiable even from an external third party. In this case, using transcript error. First, the goal of availability is the same as mentioned above. It does not assume that the client itself is dishonest. Honest client randomly assign honest and dishonest when client divide a group. In other words, the proportion of dishonest in the whole and the proportion of dishonest in the group will be similar. Thus, one group will have about 3f over m, this value pairs, so the threshold will be f over m plus 1, this one. This guarantees availability with a very high probability and shows it in later evaluation path. As before, by setting the threshold, Adversary control the group of less maximum n-1 and get the threshold of the maximum n-1 group. But after all, adversary can't recognize that because adversary can't get the encrypted value for at least one group. So output that remains unknown to the adversary until step 7. Due to the previous attribute, at least one group cannot be predicted or manipulated, and therefore cannot be manipulated to make it a biased value. So adversary cannot influence the value of the random output z. Verifiability can be satisfied with the transcript L. Transcript L contains all the message of the protocol process, so it can be reconfigured through the previous verification step. Also, to manipulate it, you need to know the secret keys of all participants, so it is impossible to generate this transcript L by manipulation. And random hard is continuous random value beacon. So this protocol make a group and select causality leader using random hound. They first proceed random hound protocol to make some random seeds. And after select causality leader, he proposed to make a random value with other group's leader and repeatedly create a random value as a beacon. And there is some paper about scalar randomness, and they use improved version of PVSS. They have lower verification complexity and can be used to reduce complexity of random from O square of Cn to OCn. Now is evaluation step. Landhound and Landhound both evaluate how well they work with large pairs, and it also checks generation, latency, and computation cost. Also check the failure probability according to the parameter values. Experiment is in the following environment, so they make these protocols in Golang and use this environment machine. This graph shows overall CPU cost of Landhound protocol run. Measure the total cost across all server plus the cost of client that coordinate Landhound and generate the transcript. For example, 1024 nodes divided into group of 32 nodes in this graph. The complete random run to generate random list requires less than 10 CPU minute total, correspond to a cost of amount 0.02 on Amazon EC2. This cost breaks down to about 0.3 CPU seconds per server, and the client that initiate random spend about 3 CPU minutes. This graph shows about work clock time of random protocol run. In this graph, randomness generation and verification take roughly 290 and 160 seconds. This one and this one. This graph compares communication bandwidth costs for COSI and Landhound and Landhard with varying number of participants and fixed group size 32. The straight line depicts total cost, while the dashed line depicts average cost per participating servers. And for the case of 1024 nodes, COSI and Landhound requires about 15 and 25 megabytes respectively. After the initial setup, one round of Landhound among 1024 nodes require about 400 megabytes due to the higher in group communication. This can be also seen as the average per server cost is less than 300 kilobytes for Landhard and around 20 kilobytes for Cossy and Landhound. An average system failure probability Q for varying group size C to 16 and 20, 30 and to 64 and varying adversary power from P0 and 0.23 and 0.32 and so on. Note that Q on this y-axis is plotted in security parameter form as minus log 2q, thus higher point in the graph indicate exponentially lower failure. There we see, for example, that both Landhound and Landhard have a failure probability like this when P is 0.33 and C is 32. This value means to this equation, and this means like 0.08 percent point. Moreover, assuming P is 0.33, we identify the point where the system's failure probability falls below 1 percent point for a group size C is this. C is 21. Thank you for listening my presentation about scalable bias resistant distributed randomness.